So let's begin our talk on the endocrine system. We've made our way through the nervous system, and you've seen the nervous system is major communication system, and the endocrine is the other major system. And we've also seen through the autonomic nervous system that it is involved in all that housekeeping stuff, keeping us homeostatic. And so the endocrine system is also going to be a part of that, keeping the body homeostatic because it's able to communicate with other tissues throughout the body. So just like the nervous system, the endocrine system is going to allow us to communicate over long distances. Okay? Because we can have endocrine tissue that's up near our throat here, and it can talk to tissues in our toes. Okay, but the difference between nervous system and say our endocrine cells is the nervous system, the neurons talk across the synapse. For the endocrine system, the endocrine tissue or the endocrine cells are going to release, instead of neurotransmitters, they're going to release hormones. And instead of across a synapse, the endocrine system is going to release it into the bloodstream. Okay. So we get released into the bloodstream, but how do we get a response? What tissues respond to our hormones? Okay, and those are only going to be the target tissues that have a receptor for the hormone. So similar to our nervous system, right? The neuron releases neurotransmitter, but it gets bound to a receptor for that neurotransmitter. In this case, we got a receptor for the hormone. But same concept, we're still getting communication across these long distances. So we kind of already talked about this, but this looks at, remember how the neuron talks, we're talking at that synapse. So we see that's different than what we see at the hormone, where the hormone is talking throughout the blood. We are going to see some special circumstances where we're going to get what we call a neurohormone. Okay. Neuro, meaning it's released from a neuron, but hormone, meaning instead of being released at the synapse, the hormone's being released in the blood. Okay, so here's neuron, but it's releasing a hormone into the blood. So acts basically similar to an endocrine tissue that releases hormone into the blood, but in this case it is a neuron. So this slide is just an overview of what we just talked, looking at the differences between endocrine system and nervous system. Right, we got the nervous system, we've already seen that, and we just talked about those neurohormones. That's with the neuron releasing a hormone into the blood, or neurocrine. Right, and then hormones, our endocrine tissue is going to release those hormones into the bloodstream. So since we're talking endocrine system, we got to talk hormones. And what exactly is a hormone? Yeah, it's just that chemical. Just like our neurotransmitter, it's a chemical signal. Okay, but instead of this case, the chemical is secreted into the blood. And it's got to have its effect. You got to realize these chemicals are being secreted into this 6 liters of blood, so they're going to be very dilute. So they got to have a strong response at low concentrations. Okay, but again, these chemicals are going to be secreted, and they'll be able to talk to tissues far away. Because you could have, you have thyroid, which is up here by the neck. It can be talking to cells down at your toe. So we can get this long distance of signaling, and you can imagine how much diluted it is, so it must have an effect at low concentrations. What are these hormones going to be used for? Well, growth and development, metabolism, reproduction, but kind of the one we've focused most on this. We've seen this with the autonomic nervous system, has controlled a lot of our housekeeping. hormones are also going to be involved in that homeostasis, that regulation of the internal environment. And what's their effects? They can be varying effects depending on the hormone, what's going to be the effect of the tissue. And you can see can transport ions, enzymatic, gene expression. We'll see a little bit of these when we start looking at the signaling of the hormones in just a little bit. All right, so if you can just memorize all of this slide, that would be great. No, but just a joke. We will be. There is quite a bit of this that you'll need to know. Okay, but we'll go through mainly the major hormones throughout the body. Some of the lesser knowns we'll stay away from, but we're going to get into the bigger and especially the hormones that are going to be from the hypothalamus and the pituitary and what they control. So we will be going through a substantial amount of this. This kind of cheat sheet or overview for you, along with what we see here. So we got quite a bit to get through, but like I said, we're going to focus on more of the bigger ones in the endocrine system. So before we get into all the different hormones, let's look at what would cause a release of hormones. Because like probably a classic one you guys are familiar with is insulin. Insulin decreases blood sugar. So do you always want to have insulin out? Do you always need to be decreasing blood sugar? If you're not eating food, your blood sugar is not going up, so you don't have to constantly secrete insulin. So let's see what are some of the stimuluses to cause a release. A humoral stimulus, this one here. Okay, it's concentrations in the blood of certain molecules. Here we're looking at calcium. We're looking at the parathyroid. That's going to help control calcium. Okay, when calcium levels get low, okay, parathyroid hormone is involved in bringing calcium levels in the blood back up. So that would be a good time to release parathyroid hormone. So the levels of the calcium in the blood are the stimulus to cause parathyroid hormone to be released. Okay. We can also have a neurostimulus. This we've seen before. We've seen this. This is that special situation we saw in the autonomic nervous system. Okay, what's causing the release of this epinephrine? It is a signal from that autonomic neuron. So hormones can be released by stimulus from the nervous system, from a neuron. Okay, the one we're going to be talking about probably substantially is a hormonal stimulus. We can have hormones that actually cause a release of other hormones. Okay, we're going to see this with our hypothalamus and our pituitary. Many of the hormones that are secreted from there are hormones that cause the release of other hormones. So the stimulus for the release is a hormone. So once the hormone's been stimulated to be released, it'll travel through the blood, and then ultimately it will find the target tissue, right? But what tissues are the target tissue? Only those tissues that have a receptor, okay, are the target tissue. So what's the response by the cells? Okay, it's variable because we can have various receptors for it. Okay, and that's going to give us our response at our tissue. So we first get a stimulus, we get the hormone stimulated to get released, travels through the blood, and ultimately find that receptor. Okay, similar to our nervous system, remember our neurotransmitters get released, bind to the receptor. Now, do we always want that hormone out in the body? We want it released, have its effect, and if we don't need it anymore, what has to happen? Yeah, we have to get rid of, terminate the signal. Okay, many of those, remember these hormones are in the blood, so there are enzymes out in the blood or at other tissues in which they will degrade those hormones. Okay, so the hormones get released, okay, travel through the blood, bind to the receptors, and then we're going to get them degraded so we can remove the signal. Okay, if we need another signal, we're going to have to release more hormones, but we do need to get that termination of hormone. So the hormones that these endocrine organs can release can come in different varieties. So let's look at some of the classification of hormones. Okay. We can look at chemical structure. What is it made out of? So what's the structure of the molecule? Okay, just like our neurotransmitters, many of our neurotransmitter, okay, polypeptides or proteins. Okay. So these we got to have genes for. We have a gene for insulin, we have a gene for growth hormone, okay, but these are longer chain of amino acids. We can have glycoproteins, okay, follicle stimulating is one of those, but these again are proteins, so we got to have genes for them. And then they'll have, instead of just a straight protein, they'll also have carbohydrates bound to it. Okay, a large group of hormones is the steroid hormones. Okay, your reproductive hormones, estrogen, progesterone, testosterone, cortisol, your stress hormones are all steroid hormones. And what steroid hormones are what they're derived from, and that is they are derived from a cholesterol molecule. These hormones look very similar to each other. They're just small modifications to the cholesterol molecules. Right? And then we have amino acid derived hormones. Okay, modified single amino acids, tryptophan, tyrosine. Okay, similar to our neurotransmitters. We saw neurotransmitters created from these. Tyrosine, epinephrine hormone. Okay, we'll also see thyroid hormone is created from a couple molecules of tyrosine. Okay, so that's classification by chemical structure. We can also look at actions of target, where the hormones will act. We can have polar and nonpolar. Imagine polar. Would polar be allowed to go through the cell? No, polar molecules, larger polar molecules aren't allowed to go through the cell, so for these, the actions are going to happen at the membrane. We're going to have a receptor on the membrane to get a response, okay? Because those polar molecules are not allowed into the cell, whereas nonpolar molecules, these are classically your steroids, are the most classical of these nonpolar. They can zip right through the membrane. So instead of having to have a membrane receptor like our polar molecules, the nonpolar can have receptors inside the cell, inside the cytoplasm or inside the actual nucleus of the cell. Okay. So that's classification by where the action is taking place for the hormone. Right, so many of our hormones, not many, but there are some hormones that actually get released in what's called pre-hormones. So they are not the actual active hormones. So the endocrine cells release pre-hormones. These pre-hormones won't have an effect at the target tissue. They don't bind to those receptors. Okay? What happens usually with the pre-hormones is they make their way to the target tissue and then get converted to the actual hormone. There's an enzyme that will convert them. Okay? Testosterone is a pre-hormone. DHT is the actual hormone that's going to have an effect at the tissue. Another classic, thyroxine. Okay, T4 we'll talk about in pretty good detail. for thyroid hormone. T4 is a pre-hormone, and when it gets to the tissue, it gets converted to T3, which is the active hormone. So pre-hormone is just a hormone that gets released in a non-active form, but then, as we see, it gets converted at the target tissue to its actual active form. So many times hormones don't work just individually, they'll work in concert or against other hormones. So let's take a look at some of the interactions that can take place between different hormones. We're going to look at 3 different types. We're going to look at synergism, permissivism, and antagonism. Okay? So synergism means that 1 plus 1, kind of concept 1 plus 1 doesn't equal 2, means 1 plus 1 equals much more than 2. Okay? So they have basically a greater effect, an additive effect, rather than just simple regular 1 plus 1 effect. And that you can see in this chart here, you're looking at blood glucose levels. So how much glucose is in the blood? Okay? And over time. Here, you're looking at if you just put cortisol by itself, okay, not such a huge drastic rise in glucose. Glucagon also increases blood glucose, but not super drastic. And then you see the green epinephrine. Those are the individuals. Now if we put glucagon and epinephrine together, this plus this is a little bit greater. But now let's add cholesterol with it, and you can see this has a much more dramatic effect on blood glucose levels. So that's an example of synergism. Another interaction is permissiveness. Okay, this is where a hormone won't have its full effect unless another hormone is available. So this other hormone must be available for the one hormone to have its full effect. We see this with maturation, sexual maturation, or reproductive maturation. Okay, you got to have the reproductive hormones, okay, to get full reproductive maturation, but you won't, even if you have the reproductive hormones, you'll get delayed development or maturation of the reproductive system unless you have thyroid hormone. So you need to have thyroid hormone to get full maturation of the reproductive hormones or reproductive glands. Yeah. So that's permissiveness. And then lastly is antagonistic. So antagonistic, we're working in opposition of each other. You see, classic example is we got on one side we got insulin, okay, on the other side we got glucagon. You're all probably pretty aware insulin brings down blood glucose where glucagon brings up glucose. So these two are working competitively or against each other, antagonistically. All right, when you eat a bunch of sugar, of course, insulin is going to be secreted, and you need to bring the blood glucose down. So insulin allows cells to take up glucose and brings it down. Okay, if you don't eat for a long period of time, your blood glucose is going to drop, and then that would signal glucagon to get released, which works antagonistically to insulin, has the opposite effect basically. So those are some of the interactions we see with our hormones. So looking at mechanisms of hormones, we've already discussed, right? The target cell must have the receptor for the hormone. It's usually specific for the hormone, can bind it with high affinity and low capacity, just meaning that at low concentrations, the hormone can have a strong effect at the tissue. And also what dictates where the hormone acts, the kind and location of the receptor. So if you remember, the polar hormones, where would they have to act? They would have to act on the membrane. So we've seen some membrane signaling already. We've seen G protein coupled receptors. We've seen the cyclic AMP signaling and so forth. So I'm not going to focus so much on membrane, but I want to focus on the nuclear receptor. So if a hormone is nonpolar, it can make its way through the membrane. So those receptors can be inside the cell or even in the nucleus. So I'm going to focus on the signaling on those since we haven't seen that yet. Okay, and the classic nuclear receptors respond to steroid hormones. Steroids are made from cholesterol, a small, very nonpolar molecule, so it can zip through the membrane. And if you look at some of the hormones, okay, steroid hormones, you can see they are just a modification. They're not too far off from the structure of this cholesterol, so they are very nonpolar. Okay, so they can zip through the membrane and they can hit receptors that are, again, inside the cytoplasm or inside the nucleus. So with nuclear receptors, we're talking about lipophilic, so non-polar hormones that can zip through the membrane and get into the cytoplasm or into the nucleus. Okay. Typically, they are not dissolvable so typically they have a carrier protein. Because they are non-polar, they don't like water, and blood is basically a solution of water, that blood plasma. So they don't like to dissolve. They like to go on together. So these hormones have carrier proteins that help them dissolve and allow them to travel through the blood. Okay. They're going to disassociate from the carrier proteins when they get to the target tissue. Okay. And there are two families. We're going to focus mainly on the steroid, but there is the thyroid hormone family, and that is what you see here, is thyroid hormone. They just vary, just differ a little bit, but they're still going to have a very similar response in how the tissues respond. Okay. So binding to a nuclear receptor. Okay. In a nuclear receptor, there are two parts of the receptor. This is the whole receptor here. There is an LBD, that is the ligand binding domain. So that is what's going to bind to the hormone. That is where the hormone is going to bind. Okay, again, this is a thyroid type family. We're going to look at the steroid here in just a second, but they both have this ligand binding domain, and then DBD here is the DNA binding domain. Okay, and so when these receptors are bound to the hormones, they are going to initiate, they're bound to DNA. So they have a DNA binding domain. They are bound to DNA. And what is DNA? It has genes. So these receptors are going to, when bound, are going to turn on the making of a certain gene. And what's a gene? A gene is going to make a protein. So these nuclear receptors' effects at the cells are to increase the production of different proteins. Okay, so again, we're going to focus, I'm going to show you specifically the steroid family, but ultimately at the end, they're going to end up causing production of a protein. Okay. Another characteristic, so now we're at a steroid hormone. Okay, here's a steroid. Okay. In this case, for steroid hormones, the receptor is located in the cytoplasm. Okay. And you see the steroid bound, and what there is at the DNA where they bind to the DNA, there are what's called half sites. Okay, because what you need at the half sites are actually two bound receptors. So what happens when the steroid hormone binds to the receptors actually dimerize. Okay, dimerize at those half sites. Okay. So once we have that two bound receptors there, we'll get the transcription. That'll induce the transcription and then ultimately making proteins. Okay. So let's walk all the way through. All right, we get a hormone, steroid hormone. Okay. And remember, they're nonpolar, so they don't want to be dissolved in this blood. So they have protein carriers that help them dissolve so they can travel throughout the blood. But once they get to the target tissue, the steroid hormone is released. Okay. And it travels in to cytoplasmic receptor or nuclear receptor. And we need two though. So we're going to have coming in, they're going to dimerize, right? And we're going to dimerize at that half site at whatever gene there is. Okay, it's not all genes. It is a specific gene that have these half sites for the steroid receptors, the bound steroid receptors. So we get binding, and then what happens is we get transcription. All right, and from our early days, we get transcription, moves to translation at the rough ER, and go through the Golgi, and we get our new protein. Okay, so hormone comes in, binds the nuclear receptor, we get dimerization at the half site of the DNA. That's going to induce transcription or whatever gene. We get the transcript, we get translation, and then at the end, the effect of that hormone is the production of new proteins. So you can see these hormones proteins are long lasting typically, right? When we've seen the neurotransmitters, what do we see? We see a cell has a response, but then it goes away rather quickly. So the response of a neurotransmitter is very quick, where here you can see these hormones can have a long-lasting effect. Okay, they may be slower to have a response, where the neurotransmitters running through a neuron is rather quickly, but the effect of hormones can be long-lasting. Okay, so that's the nonpolar. We've already seen, so similar to those neurotransmitters, we've seen those membrane receptors act through cyclic AMP. We've seen phospholipase C. We've seen tyrosine kinase. We've seen this signaling. Okay, so I'm not going to rehash all that signaling, but remember there are polar hormones and they have receptors, but the receptors can respond in different ways. Okay. So let's now start our jaunt through all the different endocrine glands and endocrine hormones of the body, and we're going to start with the major, or basically the main player of the endocrine system, kind of regulating much of the endocrine system, is the hypothalamus. You've seen the hypothalamus in the autonomic nervous system. It's a region that helps control much of what's going on in the autonomic. Okay. And we're going to see the hypothalamus is a large player in controlling what's happening hormone-wise in the body. Okay. We're going to see there are two regions that talk to the pituitary. So the hypothalamus is going to be linked with the pituitary gland, in controlling the hormones throughout the body. Okay? And we're going to see the hypothalamus can releasing or inhibiting factors. So it can release hormones that cause release of other hormones, or it can cause hormones that inhibit the release of other hormones. Okay? There's two parts. The anterior, so when we start looking at the pituitary, you can see these cells here. Okay? They extend these neurons that start in the hypothalamus, extend down into the posterior pituitary. Okay? So the posterior pituitary is actually made of axons from the hypothalamus. So the posterior pituitary hormones are actual neurohormones because they are going to be released by these neurons that originate in the hypothalamus. And so we've seen posterior pituitary is extensions of that hypothalamus. Okay, we got neurons coming in, and the axons are traveling down and making up the posterior pituitary. Okay, there's the anterior pituitary is actual endocrine tissue. So they are cells that are endocrine tissue. They are not axons of the posterior pituitary. We are going to see that these endocrine cells here, though, are controlled by the hypothalamus. So again, anterior pituitary, also known as adenohypophysis. The posterior pituitary is known as the neurohypophysis because it is made, posterior is made of neurotissue, where the anterior is made of actual endocrine tissue. So neurohypophysis for the posterior, adenohypophysis for the anterior pituitary. Remember this hypophysis name because we're going to see this shortly. It goes so let's look first at those hormones that are being released through the posterior pituitary that are being released by those neurohormones. So these are both neurohormones because they're being released by a neuron. Cell body for the neuron is up in the hypothalamus, but the axons extend down into the posterior pituitary, and these neurons are going to release the hormone directly into the bloodstream. Two hormones here. We got oxytocin and vasopressin. The other name for this, the one you'll hear, I should actually have it here, but antidiuretic hormone, ADH. Vasopressin is the same thing as ADH, just this is the older name of it. But these two hormones get released by these neurons here. Alright, so let's look at oxytocin is one of those hormones that gets released. Oxytocin is known for that ejection of milk. You guys have also, if you remember, our positive feedback loop. Oxytocin was that because there's cervical stretch causes oxytocin to release. Oxytocin causes uterine contractions, more cervical stretch, more oxytocin. So it's uterine contractions, also milk ejection. May play oxytocin is also known as the cuddle hormone. So when you're telling your boyfriend or girlfriend, oh, Schmoopy, I love you, then you probably have oxytocin coursing through you, called the bonding hormone. Okay, but also involved in uterine contractions and the injection of milk. So the second hormone coming from the posterior pituitary, and again, for the rest of the semester we won't be using vasopressin, we'll be using antidiuretic hormone. They are the same molecule, that vasopressin is just the old name. But from now on, antidiuretic or ADH is what we'll be calling, because we will be seeing this hormone. A lot of these hormones we'll just see through the endocrine system, but this one we're going to see quite regularly. We're going to see it in the cardiovascular. But for our purposes now, for endocrine system is regulate water balance or reabsorption of water. Okay, this is what you want to, if you're out in the desert and you don't have any water, this is the hormone that's going to help you hold on to that water. Instead of producing this large urine, you're going to produce a small amount of urine and you're going to reabsorb it. So ADH is the hormone that is causing that. All right, so now let's get into the big daddy, the anterior pituitary. And we're going to see a portal system. Portal system, typically blood vessels, it runs from the arteries to a capillary bed and then to the venous system. In a portal system, you have arteries, a capillary bed, a vein that attaches to another capillary bed, and then to the venous system. So you have two capillary beds in series. And so since we have the name portal system here, we're going to have two capillary beds. Okay, and where are these capillary beds located? One's around the hypothalamus, because hypothalamic, and the other is around the hypophysio. Hypophysio, remember, is another name for the pituitary, and in this case it's the anterior pituitary. So capillary bed around the hypothalamus, and the second capillary bed around the hypophysis, the anterior pituitary. Okay, and you can see that down here. Here's the first capillary bed, and you're going to see these neurons of the hypothalamus secrete neurohormones into that capillary bed around the hypothalamus. They travel through this portal vessel, and then they reach the cells of the anterior pituitary, and that's the hypophyseal part, the capillary bed here. Okay, so the hypothalamus is going to secrete hormones into this capillary bed. Those hormones are going to come down and either inhibit or cause the release of hormones from these cells here. Okay, so we got to look at what hormones are being released by the hypothalamus and what hormones are being released by the cells here in the anterior pituitary. Okay, and we're also going to see later on, we'll see portal system, we'll see the kidneys and digestive tract. You probably remember the hepatic portal system we saw in the digestive tract when you looked at anatomy. Okay, but portal system, just two capillary beds in series here. Okay. So let's look at these anterior pituitary hormones. And again, these hormones, okay, are going to be caused to release by hormones from the hypothalamus. Okay, 6 major ones. We got the ones missing here, the MSH, melanocortin stimulating hormone, but we got adrenocorticotropic hormone, TSH, thyroid stimulating hormone, growth hormone, follicle stimulating hormone, prolactin, and luteinizing hormone. Good news is most of these have basically a name that kind of gives you an idea of where they're going to work or what they're going to do. Okay, and then you see the different target tissues for the hormones here. Okay. So again, those anterior pituitary hormones are going to be controlled by the release of those hypothalamic neurohormones. So those neurons in the hypothalamus are going to release hormones into that first capillary bed, and then they're going to travel down through the portal vessel down to that second capillary bed that's around the anterior pituitary. Okay, and so that makes the hormones, those hormones that cause the release of other hormones, are tropic hormones. Okay, so those hormones in the that release from the hypothalamus that control the release of hormones in the anterior pituitary are tropic hormones. Okay, so we're going to see the hypothalamus has releasing and inhibiting hormones. Okay, and those releasing or inhibiting hormones are going to control the release of hormones at the anterior pituitary. Okay, you have growth hormone releasing hormone from the hypothalamus. Luckily, these are given in the name, right? That's going to cause the release of growth hormone from the anterior pituitary. Okay, but it's these hormones from the hypothalamus travel down that second capillary bed, and then they're going to control the release of hormones here at the anterior pituitary. So here's a snapshot. You can see here are those hormones. Those are the releasing or inhibiting hormones of the hypothalamus. And so those are the ones that are going to get released here. Then these hormones here travel down to there and cause the release of some of these hormones here. Okay, gonadotropin releasing hormone, GnRH, is going to cause a release of follicle stimulating hormone and luteinizing hormone that we'll be talking about. Okay, growth hormone releasing hormone released by the hypothalamus cells is going to cause a release of growth hormone. Corticotropin releasing factor or hormone is going to cause a release of adrenocorticotropic hormone. And then thyroid releasing hormone, thyrotropin releasing hormone is going to cause the release of thyrotropin, or what we call TSH. Okay, and then dopamine can control the release of prolactin. Okay, but these ones that are controlling the release are tropic hormones. Okay, and we're going to see many of the hormones that are released by the anterior pituitary are also tropic hormones, because what does TSH do? It goes to the thyroid to cause release of thyroid hormone. ACTH, adrenocorticotropin releasing hormone, goes to the adrenal gland, the cortex of the adrenal, so adrenocortex, to cause the release of cortisol. And GH, when we go to the liver, cause release of insulin growth-like factors. And then FSH, LH can also control the release of these hormones. So these would also be tropic hormones. Okay. Tropic hormone meaning that they cause a release. Their target tissues are other endocrine glands that cause a release of other hormones. So this gives us what we call hypothalamic pituitary axes, these axes, because we have, what do we have? We have response, we have hypothalamus gets released, okay, cause a release of hormones at the anterior pituitary, okay? But remember, we also don't want to continually release hormone, okay? We don't continually want to release growth hormone. You know, we need growth hormone for growth and repair, but do we continuously want to release it? No, we want to turn it off. So we are going to have these negative feedback loops. Okay, told you this would be coming back throughout the semester, so we got to talk our negative feedback. This is going to keep the levels of hormone homeostatic. So let's look at the hypothalamic pituitary thyroid axis. Okay, remember, thyrotropin releasing hormone causes a release of TS, goes to the anterior pituitary, causes the cells of anterior pituitary to release thyroid stimulating hormone. Thyroid stimulating hormone will go to the thyroid to cause release of T4 and T3. Remember, T4 is that pre-hormone, okay, and then T3 is the actual hormone. So most of the hormone that gets released by the thyroid is T4, okay, the pre-hormone, okay, and it's going to have effect, but we don't want the levels of this to get extremely high. Okay, so how do we stop this? And how do we stop it? It is through negative feedback. Okay, high levels, T4, T3. T4 will go back and signal at the anterior pituitary and shut off the release of TSH. It also, high levels of T4, T3 would go back and shut off the release of TRH. So if we don't release TRH, we're not releasing TSH. If we're not releasing TSH, then we're not releasing T4, T3. So we can see this negative feedback keeps us homeostatic. Let's look at another hypothalamic pituitary loop. Okay. GnRH, gonadotropin releasing hormone, causes the release of LH, luteinizing hormone, and causes the release of follicle stimulating hormone. They, in turn, they work on gamete production, but LH also causes release of testosterone, progesterone, estrogen. Okay, so now we got these here. So how do we keep this regulated? We don't want to keep spewing out LH, FSH, and keep doing this over and over. So we need a mechanism to turn it off. That's where our feedbacks. Let's look at this. This varies a little differently because what did we see before? We saw this in thyroid stimulating hormone is we had those hormones from the ovaries can act at the anterior pituitary to inhibit release of this, LH. All right, no LH, then we don't have steroid production. But those steroids can also go back and inhibit the release of GnRH. If we don't have GnRH being released, we won't have LH, and we won't have steroid hormones being released. This differs a little, so this all was the same as what we saw in the thyroid, but we have an added feedback. These would be considered what we call long loop feedback. Okay, going from the actual end endocrine organ coming back to shut off. Here, LH can go up. If LH levels get high, it can go up and shut off the GRH. This would be what we call short loop negative feedback. Okay, we didn't see that in the thyroid hormone, but we see that here in the GnRH. Okay. So a couple other hormones we see from the anterior pituitary. That's our prolactin and growth hormone. Just going over prolactin, we saw what he milk lactose. So milk production. Okay, also has some effects on the immune system, but you remember mainly milk production. Okay. And then growth hormone, pretty obvious, affects metabolism and growth and repair. But again, these are controlled by hormones from the hypothalamus. All right, so let's look at adrenal glands. Okay. We've seen this portion. We saw that in the autonomic, right? That's actual nervous tissue. Those modified chromaffin cells that release the epinephrine. And we're going to talk about this is actual endocrine tissue. Okay. One of the major hormones we talk about will be cortisol. That's your major stress hormone. Another one that we will be talking a lot about is aldosterone. Comes from this cortex. Okay, this cortex is all endocrine tissue. And we can see some of the hormones, mineralocorticoids, okay. Aldosterone. We will talk about aldosterone. Aldosterone is going to be sodium reabsorption or retention, and in turn water. Okay, we're going to be, where did we see this before? We saw ADH causes water reabsorption. So aldosterone and ADH have somewhat similar functions. That cortisol, and what stimulates the release of this cortisol, right? That ACTH, that hormone from the anterior pituitary. Okay, so adrenocorticotropin hormone is going to go to the adrenal cortex to cause a release of cortisol. The cortisol is a common glucocorticoid. And see, it suppresses inflammation, okay. And then extra androgens, so steroids, they get released by the reticularis here. Okay. Mineralocorticoids get released up here, the glucocorticoids through here, and then zona reticularis would be basically this is supplemental, like testosterone and estrogen. Chiefly we get them from the ovaries or the testes, but there is some supplementals that are getting released here. Okay. So this is just showing the synthesis, the pathways through the steroids. Okay, you don't have to memorize any of this. This is just showing kind of the flow and where these hormones come from. Okay, but they're all actually derivatives of cholesterol. Okay, so they are non-polar hormones. Let's look at that control of cortisol. Because remember, cortisol is controlled by release of ACTH from the anterior pituitary, and ACTH controlled by the release of corticotropin releasing hormone from the hypothalamus. So you can kind of see this is the HPA axis, hypothalamus, pituitary, adrenal axis. It's hypothalamus, pituitary, and adrenal. But you can see we have those long negative feedback and short loop negative feedback. You can see secretion. This is a common, not common, but cortisol. If you have high-grade inflammation, this is one of the great ways to get rid of inflammation. Although you gotta realize when giving hormones as drugs, you're giving cortisol. So you're giving them an artificial form to help relieve inflammation. But if you give cortisol, what is that going to do to the pituitary gland and the hypothalamus? Because that artificial cortisol is going to negatively feedback here and negatively feedback here in the patient's body. Okay, so you're getting rid of the inflammation, but you're also creating negative feedback. Okay, so you start shutting this down. And your body, if you have this for long periods of time, you're going to continually be shutting down this pathway here. So at the end of the day, if you were to pull somebody off of cortisol quickly, you gave them cortisol for a long period of time, and then you just pulled them off, what do you think is going to happen to the natural cortisol production in that person? Yeah, it's been constantly negatively fed back. So if you just pull the person off of cortisol right away, they would have a substantial drop in cortisol levels. So that's why when giving hormones as drugs, you got to be careful. What they would typically do, instead of pulling somebody off quickly, they will taper them off. Say you were taking 5 milligrams. They would just have you take 4 milligrams for a couple days, 3 milligrams for a couple days, 2 milligrams for a couple days. So you're slowly taking them off the cortisol because that will allow the person's natural cortisol production to get back in line. Because if you pull them off drastically, they're going to have a crash of cortisol levels. Okay, so you got to be very careful with these hormones. Another classic example of this is what is a common drug that people take for weightlifting? Yeah, testosterone. So this would be testosterone at the end, and you had LH and gonadotropin releasing hormone. If somebody's constantly shooting themselves with testosterone, they're shutting down their own systems. So does the testes have to make testosterone anymore if somebody's constantly shooting themselves with testosterone? Yeah, for a man, you may have heard that they get small berries when somebody that takes testosterone because they are shutting off their own production of testosterone from the testes. Okay, so you've got to be careful with these hormones because they have this long-term drawn-out effect. So you can see this is what we're talking about. This is that drawn-out effect. Here's the exogenous. That would be the drug or the giving them cortisol as a medicine. You get the target tissue response, you get that inflammation down, but you're constantly turning off that negative feedback. Okay, so if you pull them off drastically, they would have low cortisol levels. Okay. And we already talked about androgen, right? Because that would be testosterone there, LH, and gonadotropin releasing hormones. And you would have low testosterone in that case if you were giving exogenous testosterone. So let's look at closer look at our thyroid gland. We already kind of looked at the feedback loop, but we're going to look at it even closer and look at exactly what's being produced in the thyroid. Okay, we got several cells, parafollicular cells and follicular cells. Those are the ones that are surrounding this follicle. Okay, this is the follicle here. Parafolliculars are out away. The follicular cells are the ones that are sitting next to this follicle. Because you actually get two hormones from the thyroid. Okay, the follicular cells are going to produce the thyroid hormone. And by thyroid hormone, we mean that T4 or T3. Okay. The parafollicular cells, okay, are going to secrete calcitonin. Okay. Calcitonin is involved in calcium levels in the blood. Okay, so they're going to cause reduces plasma calcium. Okay, so two hormones. We get thyroid hormone from these follicular cells, and we get calcitonin from these parafollicular cells. So what's the effect of thyroid hormone? Okay, the main effect we'll see is on its basal metabolic rate. Okay, your BMR. And so in the old days, if you were overweight or you wanted to lose weight, thought, oh, maybe you got low thyroid hormone. That's causing you have a low basal metabolic rate, therefore you're gaining weight. So let's give you thyroid hormone, and we can increase your basal metabolic rate. Of course, you would lose some weight. Fortunately, we got a lot of other factors or other things that the thyroid affects. Okay, one also heart rate. You would have, if you gave excess thyroid hormone, you would have a racing heart, you'd be jittery, anxious, you'd be sweaty, because this thyroid hormone has other effects throughout the body. Okay, but the main draw is that basal metabolic rate, the BMR. So here is the hormone that follicular cells are going to create. You can see there is thyroxine. That's the T4 we're talking about, T4. Okay, and what does the 4 represent? This is iodine. Okay, so iodine is in this thyroid hormone. In this thyroxine, T4, there are 4 iodine molecules. Let's look at the actual active hormone, because this is the pre-hormone. Most of what gets released by the thyroid is this pre-hormone. Okay. But let's look at triiodothyronine, T3 for short. What do you see different from here? Now we only have 3, so basically we remove an iodine and we get the active form. Okay, so iodine is essential for you to have active thyroid hormone. So let's look at some disorder of this thyroid hormone, and this is going to show us kind of our negative feedback and the importance of it. So we could have disorders of thyroid. We can have hypothyroid or hyperthyroid. Okay, we can have disorders. We'd have, like I said, pulse rate would be rapid if you had hyperthyroid, excessive perspiration, you have increased activity, decreased sleep because you're just ramped up. Okay, and where hypothyroid, if you had low levels of thyroid, basically the opposite effect. Okay, how can we? One other factor in a thyroid disorder, besides hypo or hyperthyroid, you could get what's called a goiter. This is basically an enlarged thyroid gland. Okay, you can get this goiter when you have hypothyroidism, okay, where you see iodine deficiency, or in Graves' disease, you would have actually hyperthyroidism. But these both could result in a goiter. Let's see how. Looking at this here, why would iodine cause this goiter? So what did we need for proper thyroid hormone? Right? T4, T3, the 4 and the 3 represent the number of iodine molecules. So you must have iodine to make functioning thyroid hormone. If you're low in iodine, you are not making functioning thyroid, or very little functioning thyroid. So you would have hypothyroidism. You would have the effects of hypothyroidism. But why would you get a goiter? Because remember, T3, T4 go back and turn off TSH and TRH. Okay. This TSH is tropic because it causes a release, but it also has a trophic effect. It will increase the size. So if you have TSH talking to the thyroid, you're going to get it to increase in size. And if you don't have iodine, you're not making functional this, or very little functional T3, T4, and you won't be negative feedback. You won't have your negative feedback. And that means this continually gets released, TSH gets released, and TSH keeps talking to the thyroid to try to keep making thyroid hormone, because your body's saying your thyroid hormones are low. So it's going to tell your thyroid. And as TSH is continually stimulating the thyroid, you get a growth of the goiter. Okay. On the other, the Graves' disease, okay, you would get hyperthyroidism. So you have iodine, so you can make functional T3, T4, but this is a disorder. It's an autoimmune disorder. Okay. You're making antibodies. Your immune system, okay, we're going to talk about it later in the semester, makes antibodies. In this case, it made an antibody, and not everybody does this, but some disorder, if you get an antibody that acts as, basically mimics TSH. So this antibody is basically acting the same as TSH. And what does TSH do? It tells the thyroid to keep making thyroid hormone. The problem is these antibodies are not part, this is part of the immune system, it is not part of this feedback loop. Because you can see if we have lots of thyroid hormone, we're actually getting lots of negative feedback. So in the Graves' disease, you saw up here, TRH, TSH is high, but TRH and TSH are low because you are getting the feedback. The problem is this antibody is acting as TSH, so it's continually stimulating the thyroid, and you get yourself a goiter. Okay, so this is classic because this basically makes you guys understand how the negative feedback works. Another hormone, parathyroid. So on the back of your thyroid, there are 4 little dots, 4 little clusters of cells, and they secrete parathyroid hormone. Okay. What's the function of parathyroid hormone? I like to say purge because it's going to increase calcium levels. We saw the calcitonin that got released by the thyroid did the opposite. It decreased calcium levels, where parathyroid is going to increase calcium levels. Okay. You see your feedback. All right, if calcium levels are low, you want parathyroid, but what happens when calcium levels go back up? You get negative feedback. Right. Pancreatic hormones, these are the ones you probably have pretty well know. Insulin from our diabetes in the news and so forth. Okay, but you have two. You have alpha cells and beta cells, and these are in the islet of Langerhans. Because only about 1% of the cells of the pancreas are actually endocrine tissue. Okay, the rest, most of it is for digestive purposes and exocrine. So, but the endocrine glands or tissue cells, alpha cells secrete glucagon, and beta cells secrete insulin. And this is for your regulating your blood sugar, keeping your blood sugar homeostatic. Okay, and these two, we've already saw, work antagonistically. Okay, they have the opposite effect on the tissues. Let's take a look at insulin's action. Since this is one of those kind of the biggest disorder in our Western society, because this has without the insulin actions, your blood sugar levels are high constantly, and that has a drastic effect on the body. But let's see how insulin acts. Insulin's going to be when blood sugar goes up, right? Your blood sugar is increased. So you eat a bag of Skittles, your blood sugar goes up. Do you want it to stay high? No, you want to bring the blood sugar down. So if we were able to bring glucose into the cell, you would be removing it from the blood. So that's what insulin's actions are going to do. Okay, you have in your skeletal muscle and your liver, the cells have GLUT4. Okay, these GLUT4 transporters, okay, for glucose. Here's your insulin receptor. Insulin binds, it's going to signal to put. So without insulin around, these are not on the membrane. They are not there. So if they're not on the membrane, you can't bring glucose in. So if we want to bring glucose into the cell, we need to get these out to the membrane, and that is the effect of insulin. So these are sitting in the vesicles. Binding of insulin results in signaling that causes these to get embedded into the membrane. Okay, once these channels are inserted, now glucose can come in. Okay, so insulin's effect is to insert these GLUT4 channels onto the membrane. Looking at the effects, kind of the actions, the antagonistic actions. Okay, glucose goes up, right? We need beta cells, we need insulin up and glucagon down. Whereas when glucose is low, we need the opposite effect. We need glucagon up and insulin down. But once we get glucose in the right range, we're going to negatively shut off. Okay? For this part, we brought the glucose down within range. We shut off insulin release. Here, we got the glucose back up into range, and then we shoot down and negatively feedback for glucagon.